Okay, so we can start. Firstly, Merry Christmas to everyone who celebrates this holiday. And let's start with recalling a bit what we did last time. So last time we proved the Lewis theorem. Mm, doesn't work for some reason. Oh, I think because I was using the wrong window. So we established the Lewis theorem that discusses some criterion for being a Brownian motion with respect to a filtration. So what does this some filtration FT? So what does this mean? So being a Brownian motion with respect to filtration actually means some things. Firstly, this is a Gaussian process. Gaussian process with proper mean and proper variance. Secondly, increments are independent with respect to this filtration, and the whole process, it should be the first part of the statement, the whole process is progressive with respect to this filtration, so it's well measurable with respect to this filtration. And the third property is that the strong Markov property holds. So we already know that a Brownian motion is a Brownian motion in the sense with respect to its own filtration, possibly augmented, and this already discussed a number of times at the beginning of our course that augmentation of the filtration is a necessary step. It's a very natural step. It doesn't take away anything. It provides benefits, etc. But overall, we can think about a larger filtration and a process that effectively is a Brownian motion in this sense. So it satisfies everything we want from Brownian motion in this definition. And we considered example, let me recall it, of a stochastic differential equation, d psi of t equals signum psi of t dwt. And we showed that if beta is a Brownian motion, we can define as a stochastic integral with respect to this motion, another f beta t Brownian motion w such that the d beta t is exactly signum beta t dwt. And in this case, we actually showed that beta is not even adapted with respect to the filtration of W. So we started from the end. We have a solution and we found a Brownian motion that it's indeed a solution of this SDE. This is not covered by the previous theory because we always started with some Brownian motion, with some filtration, and we obtained solutions which were adapted progressively, measurable with respect to this filtration. This is a very different situation. And actually, what is interesting, if you replace the signum with just indicator of the upper half line, then we obtain a properly defined, in the sense of all the previous theory, solution. So today we are going to talk a bit about such strange situations. This is mostly a survey because we don't have time and possibility to prove those results, but it's important to know them. And later, if we have time, we will switch to actual approximation of stochastic differential, of solution of stochastic differential equations at last. So let us discuss a definition that covers this example. So a collection psi, W, and a filtration on some probability space omega f e is called a weak solution of d psi of t equals a psi of t dt plus sigma psi of t dwt. I will consider only time-independent case. You can add t here. Nothing changes in this definition. If W is a Brownian motion with respect to this filtration, this filtration is good enough, so it satisfies standard assumptions, which is right continuity and being augmented by null sets. This is technical, obviously. And psi is progressive with respect to this filtration. And 4 holds. In the sense that all integrals are defined. We do not give any assumptions on coefficients, and this may not be defined in L2 sense. The whole theory of this weak solution is outside of this theory of L2 solutions that we were interested for quite some time. So note that we're speaking about a collection. Obviously, the solution in strict sense is this process, but we specify a solution, a Wiener process, a filtration, and some probability space. So here is exactly the situation as the previous example. We start by constructing a solution. We do not start with some probability space and some Brownian motion, and then we define a solution. We start by giving it. And a solution of star is pathwise or strongly, in some sense, unique if for any two solutions, weak solutions, psi k w k f t k with the same Brownian motion w, so w1 just equals w2, and on the same probability space such that they start psi1 and 0 start from the same point, we have that for we have psi1 equal psi2 on 0 t almost surely. So if you think about strong solutions that we were discussing before, this is more or less the same for them. If they are strongly unique, they are pathwise unique. However, this is a way to speak about solutions of these weak solutions. And a solution star is called unique in law, or unique in the sense of probability laws, if for any two weak solutions, psi1 and psi2, their distributions, that is, the image of the original probability measure under this mapping, are equal on the space where they actually live. The important thing is that these are two different things. So we already discussed that in this situation you can produce two different solutions by switching the sign of one of these Brownian motions, and they're not going to be pathwise unique, but their solution is still going to be the Brownian motion, because we discussed that the solution of this equation is always a Brownian motion. So this is an example of equation which has uniqueness in law but doesn't have uniqueness in the pathwise sense. So every strong old solution is obviously a weak solution. And actually, one interesting and characteristic feature of strong solution is that they are actually functions of the initial condition and the whole trajectory of the Brownian motion used in this SDE. And this is observations that we will revisit later a bit. Now, one can say that weak solutions are very natural in the sense of applications, because in general, you do not observe any Brownian motions. You always observe the resulting process, and you are effectively interested in some functionals of it, some properties of it. On the other hand, if you start with a model, strong solutions seem to be a preferable way, but obviously this is a very rough way of thinking about them. These are two very separate branches of probability. And the theory of weak solution is effectively the theory of such things as martingale problems. Unfortunately, we are going to discuss them, but one remark that is interesting is that martingale problems deal with devices of such form f psi of t minus 0 of t af psi of s ds, where psi is a weak solution and a is the operator. In one-dimensional case is going to be of this form, d over dx. So because they deal with such expressions, for instance, time change is very easy to do here. And it's easier to do compared to the case we had last time, because last time we need to care about time change in stochastic integrals. But here, stochastic integrals are not going to be involved. This is the meaning of my remark, that it wasn't the best place to do time change. However, it's still a very important technique, and we need to know about that. Now I will only cite a few results about weak solutions, so we have some setting, and I will briefly discuss where you can read and what is the difference in terms of techniques compared to the case of strong solution. So I will consider multi-dimensional stochastic differential equation. Right now with zero assumptions on coefficients. I am not making any assumptions on coefficients. I'm considering only time-independent case, but the theory covers also situations where there is some dependence on t here. So coefficients are not homogeneous. dwgt, where k ranges from 1 to d, and w1, w D are Brownian motions. Now, note that when we speak about weak solutions, this is effectively a formal expression because we know that these Brownian motions are not even defined. When we speak about strong solutions, they are given from the beginning. But right now, we're asking for a pair of Xi and W that this holds. And the theorem that illustrates the whole theory is consists of two parts. So let drift be measurable and bounded, and sigma be just continuous. So no Lipschitz continuous assumptions, etc. Then there exists a weak solution. So these assumptions are very weak compared to the case of strong solutions. The second part of the theorem is as follows. So set S sigma star, which is a transposition of this matrix. Let drift coefficients be again measurable and bounded. And S be continuous. And such that for any x belonging to Rm except for 0 and any y belonging to R ds y x x greater than 0. Then there exists at most one solution. They may not exist, but there cannot be multiple solutions. So there is a noticeable gap between these two statements, and that's because they are treated very differently. Now, if you speak about the existence part, the first part, at least in one-dimensional case and under some additional assumptions on coefficients, you can actually propose a proof. We already discussed that you can remove drift under very general conditions. And then, given that sigma is, say, bounded from above, you can do a time change and transform the whole driftless SDE into a Brownian motion. Now, starting from a Brownian motion and going backward in time, you can construct a solution. Alternatively, you can take drift continuous, do Lipschitz continuous approximations of A and sigma, and obtain the solution as a limit. This is another alternative. But the most general case to get rid of drift, which happens in both cases, in the case of the existence and the case of the uniqueness, is by the Girsanov theorem. That's why it's only bounded, because the Girsanov theorem works when drift is bounded. It allows you to remove drift and discuss the situation of the process with no drift. Now, so at least in the existence part, we can see some ways to do this. Obviously, they are not this easy as it sounds, but still they seem to lie within the probability theory. The existent part, the uniqueness part, unfortunately, goes outside of it. So this is condition is a ellipticity condition known from the theory of PDs, and indeed the existence of laws of weak solutions, which is exactly this, what this part talks about, is related to some properties of the corresponding semigroups, the corresponding resolvents of those semigroups, and some quite hard estimates for integrals with respect to corresponding fundamental solutions. They exist because this holds. So it goes deep into this field of PDE, I dare to say most probabilists never actually cared to read about them, so don't be afraid if you do not know what those estimates are. But unfortunately, it's not covered by probability. And it would be really, really hard to cover in any reasonable course. In contrast to the first part. The first part can be covered in our course. It would require a few lectures, but this part cannot be. So, the important conclusion that the existence of the uniqueness parts are treated very differently. That's why there is a lot of different theorems that say only about existence, or only about uniqueness, etc., mostly about existence. And weaker and weaker assumptions, but sometimes it's hard to obtain the uniqueness. For instance, even on some seminars in our department, you can see that people can prove the existence of the existence theorems for some martingale problems, for instance, martingale problems for measure value processes, but they struggle with the existence part because the uniqueness part. They struggle exactly with the uniqueness part. This is harder to do quite often. Now, references that you can consult is obviously Struck and Varadan. Multidimensional diffusion processes. This is actually the book that gives the whole theory. It's hard to read, but it's actually readable. At some point in your life, you will find that this book is actually readable. But it's very technical. Positive harmonic functions and diffusions. Now, you don't actually need anything in this book except for the introductory first chapter where it discusses martingale problems. Especially, it's very useful for discussing and studying martingale problems in domains. And we will touch SDEs in domains a bit in this course later. So you just need the first part. You don't need positive harmonic functions. Now, a good collections of results is Rogers Williams. I don't remember which volume is. I guess the second. And obviously Karadzias Shriv. Shriv. So anywhere you can read an exposition at least. But the results, if you are interested in technical details, are given here. Now we can move forward towards some technical applications. Now, what we are going to revisit here is pathwise uniqueness. So why? Because there is a theorem that says that sometimes you can know the existence from some other sources. For instance, you obtained your solution as a limit process, etc., etc. Your coefficients don't satisfy standard assumptions of linear growth or of Lipschitz continuity. But you still can work it out by using the following fundamental result theorem, that if an SDE has a weak solution, it can be obtained by any means, weak solution, and possesses pathwise uniqueness, then it has a unique strong solution, regardless of how bad coefficients. Now, this is formally stated for fixed starting initial condition. However, in general, in the theory, you consider on also random initial conditions which are independent of the Brownian process that is involved in the SDE. And there is a fairly unknown paper by Kallenberg that says that if you have this weak solution and pathwise uniqueness for any fixed starting point, you actually have weak solution and pathwise uniqueness for all starting points, including randomly distributed. So as a result, sometimes you're interested in pathwise uniqueness because it can get you a strong solution under rather mild assumptions. And also the proof, some results that we're going to discuss don't really rely on the fact whether we're dealing with weak or strong solutions, because the method is works uniformly for them. And actually the method might be the most interesting thing for us in this case. So an example of the theorem that is useful, a standard theorem that is useful, is actually this. It's one-dimensional. And actually in one-dimensional case, there is way less assumptions that make the previous theorem work. So one-dimensional case is actually much easier than multi-dimensional. So I will consider one-dimensional stochastic differential equation, d psi of t equal a psi of t dt plus sigma psi of t dwt. And I will assume the following, where A is Lipschitz, sigma is just is continuous, and exists strictly increasing function on the positive half line that starts at 0, such that sigma x minus sigma y is less than rho x minus y modulus, we need modulus, and integral from 0 to 1 dx rho squared of x is plus infinity. Then pathwise uniqueness holds. And to prove this theorem, we will actually construct another C2 approximation of the function that takes x to its absolute value. And this is a surprisingly general method that can be encountered in a number of papers all across all fields of probability, in particular in the serial numerical approximation, because people use some versions of it or just it to prove existence results for particular problems they are studying, for bad coefficients, to obtain some convergence and rates of convergence in some numerical scheme, etc., etc. So let's discuss it. Now, we start by considering an positive numbers decreasing and such that integral from an to an minus 1 dy rho squared y is n. And this is achievable exactly because of this. Now take any sequence of functions such that for any fixed n, this function is as follows. It's continuous. It lives on this interval, and it's non-negative and is less than 2 rho squared times n. And the integral from an to an minus 1 phi n psi n of y dy is just 1. It's not hard to see that such function can be obtained. Just take some function of this form, and because you have this 2, you have a possibility to achieve this. Take this as an exercise to construct them directly by using an in terms of the sequence of an. And our approximation of a modulus is as follows: dy integral from 0 to y dz psi n of z. Now, so what we have now for any n, this is 2 times continuously differentiable. Its derivative is actually less than one, because this lives on a smaller interval. So starting at some point, it just disappears. There is no reason to go above 1. And its second derivative is also controllable. So second derivative is just less than this, which is less than 2 n rho squared of modulus of x, indicator in minus 1 of x. And also, it's very easy to see, just you can check it by yourself, this holds for any x. Because at some point, you will be integrating over the whole support of this f and y. The supports became smaller and smaller, and for every fixed x, at some point, this is going to be larger than the upper limit of the support. Now we can use the Ito theorem to this phi n, which is the whole point. Let me introduce delta process is psi1 minus psi2, where psi1, psi2 are solutions. They may be strong solutions, so this whole theory works also for strong solutions from the beginning. They are just solutions with respect to one Brownian motion. We don't care about filtration, we don't care about anything. And then phi n of delta of t, actually integral from 0 to t, derivative delta of s, psi1 of s minus a, psi2 of s, stochastic part, correction, which involves second derivative and sigmas squared, and stochastic part, which uses first derivative and first powers of sigmas. So now theoretically you might need to do some localization, but we already know how to do that. Now, by taking mathematical expectation, we actually get rid of this part immediately. And now we can estimate, so this is integral from 0 to t, something ds plus integral plus mathematical expectation integral from 0 to t. Second derivative, something ds, this is I1, this is I2, and let us estimate them separately. So I1 is integral from 0 to t mathematical expectation, first derivative delta of s. It's less than. Let's take modulus everywhere. So the difference of values of our drift modulus ds. Now, we already said that this is less than 1 And we have Lipschitz continuity. So for some constant is less than the difference of size, which is exactly just delta of SDS. What about I2? I2 is less than mathematical expectation integral from 0 to t. Second derivative delta S. Now, sigmas, by this condition, the difference of values of sigmas is dominated by rho. So we can just give a rho squared delta S. ds is less with some constant, no constant. And now we have the estimate with the second derivative. So the second derivative is less than this. Integral from 0 to t, 2 over rho squared delta S times n, indicator, yes. Now obviously this cancels this with this. This doesn't matter. This is less than effectively 2tn, and this goes to 0 when n goes to infinity. So by the Gronall-Belmont lemma, we conclude that mathematical expectation delta t, which is limit fn delta t when n goes to infinity, because it's by the monotone convergence theorem, we have monotone convergence. This is exactly what we want. And this is less than limit when n goes to 0, some constant, and tn. So it's just 0. Which means that delta t equals 0 for any t, which means the probability that delta t equals 0 is true for all rational points on our interval where the diffusion, where our solution are defined, is again 1. Because this intersection of events of probability 1 over the set of indexes that is countable. But this is a continuous function. It's a difference of continuous functions. Psi1 just equals psi2 and 0 t. Now, that's effectively the proof. Remark, so a large number of extensions of these theorems, this theorem can be obtained by using a Bihari-LaSalle, if I am pronouncing it properly, which I am not, inequality. This is a nonlinear generalization of the Gronall-Bowman inequality. So just look it up to know that it exists. And standard example is actually phi of x. Oh, sorry. Sigma of x equals x to the power alpha, where alpha it is equal to 1/2. So because we know that it has weak solutions, we actually have strong solutions, even though we lose a lot about Lipschitz continuity. And this method of C2 approximations is quite general in the sense that it also produces results of this type. Theorem, this is comparison theorem. And it goes as follows. Again, one-dimensional is this. So you consider two stochastic differential equations, dt, plus sigma, the same, diffusion coefficient, the same, and the same Brownian motion. They start in this way. So the starting point of the first is equal 2 or lower than starting point of the second diffusion. And assume A1, A2 are Lipschitz. It can be quite relaxed, but to hold their continuity of proper or quite lower power, but it requires this version. And sigma is the same as here. So it's continuous, there exists rho such that this holds, and this function rho is such that this integral diverges. Is as in the previous theorem. Then, if a1 as a function is less than a2, psi1 is less than psi2. Again, if you need, you can do localization, but we already did that a number of times. You just define the time where any of it goes above some level and write down everything up to that time. And here you define new functions phi n of x, dy, dz psi n of z, where psi n's are exactly this from the previous proof, times indicators that x is greater than 0. And this is going to converge to just this. And you will use, this is going to converge. And you will use zeta formula again, and you will conclude that this holds. So this is an example how this method can be tweaked to address another types of theorems. And there is a large amount of works devoted to generalization of these comparison theorems, pathwise uniqueness theorems, for different types of coefficients. Now, at last, we arrived at the point where we can start discussing some numerical schemes. Numerical schemes. So effectively, at this point, the course is going to progress as follows. We will start discussing some numerical schemes. We introduce two types of schemes. We will study one type, and then we will switch to another type. For that, we will need to study connections between stochastic differential equations and partial differential equations. And this is most of the second part of the course, effectively. Now, references for this part is standard. So Claudin, La 10. Numerical approximation, something, something. It's very standard book. A much shorter book, which gives a very useful introduction and actually states a lot of interesting results, is Graham Tilley. I think it's Monte Carlo. It's called Monte Carlo approximations of something. The book of Milstein, not by Milstein and another author, but just by Milstein, it's also called Numerical Approximation, something like that. And the first is actually Service of Tilley. He has a few of them, like at least 3 of them. You could use Messinet to get those titles. And this is actually a very good also starting point. Now, if you think about numerical approximation, so you have some SDE. There are 2 ways to speak about approximations. So the first is strong convergence. Convergence. And it's typically formulated that you want pathwise convergence. So you seek those approximations psi n that this holds for some p, for instance, for p equal to 2, for a larger p, etc., etc. And preferably you also want to know the speed of the convergence. However, in practice, especially in the connection with PDEs, you want to speak about convergence of functionals of solutions for some functions from some class of functions. You want your solutions to converge to the mathematical expectation. These are two different approaches, and typically you can think about this in the terms of having a model and trying to understand how this model behaves. You want to know what distributions you get in the limit. You want to understand how functionals behave, what are confidence intervals, etc., etc. And this is a slightly different animal. This should be treated via a slightly different set of problems, of tools. And it's more related to the second part of the course. So we will firstly discuss strong convergence and so-called strong schemes that provide some type of this convergence. And then we will switch to connection between PDEs and SDEs. And there we will see why weak convergence is also important and how to address issues that appear in this setting, second setting. So also a remark. So if you think about this, you would effectively want to do Monte Carlo. So sorry. This is where psi n1, psi n capital are independent simulations at step n. A characteristic feature of this expression is that here we start with some Brownian motion, and here we don't really discuss any Brownian motion. So maybe in this way, and we will see this is true, you can get rid of even Gaussian random variables when discussing such examples. So standard way to approximate a mathematical expectation of some functional of a random process is to run a simulation for this random process n capital times an average. This roughly gives you the mathematical expectation, and you expect that n small goes to infinity, it also becomes small to this. So there are two sources of errors here. The first one because you have insufficient simulations, and the second one because n small is too small to provide a decent approximation. We'll return to that later. Let me check. Regardless of the way you're going to do this, the starting point is the following the Ito-Taylor or it's also called Wagner-Platen expansion. So let's formulate what it is. So I will denote a dx plus 1/2 sigma squared dx, and L1 is just sigma dx. Let us define two differential operators. We are now considering one-dimensional case for simplicity. Then the Ito formula is literally for sufficiently good function f is f of psi of 0 plus integral from 0 to t L0 f psi of s ds plus integral from 0 to t L1 f psi of s dws. This is literally just the reformulation of the Ito formula in terms of such integrals. Now, this is a new function. So we can apply a Ito formula to them, which gives us the following expression: f psi of 0, or maybe we don't. So let's now start expanding the original solution. So we have 0t a psi of s ds plus 0t sigma s psi of s dws. Now, this is our function f1, this is our function f2, and I want to use the Ito formula in this form in terms of these two differential equations to these functions. This gives integral from 0 to t a0 psi of 0 plus integral from 0 to s, because here s stands as L0 a r psi of r dr plus stochastic part L1 a, because this is for the first r psi of r dwr ds plus here we have sigma 0 psi of 0 plus integral from 0 to s L0 sigma r psi of r plus integral from 0 to s L1 sigma r psi of r dwr dws. Let us rewrite it by trying to think in the terms of small t. So what would happen if we want to get a linearized version of psi of t for small t? In the very same manner, we can do this for ordinary differential equation. This is going to give us psi of 0 plus this is just a 0 psi of 0 t plus here sigma 0 psi of 0 wt and the remainder. The remainder is going to consist of a number of integrals. The first integral is iterated ds 0s dr, iterated Lebesgue integral. Now we have two integrals ds s dr dwr L1 and By the way, here we have like a special domain of integration, but in general, you can switch Lebesgue integral and stochastic integral. You can switch places for them. So this is called the stochastic Fubini theorem. There is a number of versions of it. And you have iterated differential stochastic integral dwr L1 sigma r psi r. Now, we can now apply the Ito formula to this term, to this term, to this term. And every time it will produce us three terms. The value, a constant, Lebesgue integral, and stochastic integral. And you will continue. And under some good assumptions and coefficients, you will end with representing psi as a series of different integrals of the form. So psi is a series of integrals of the form some constant, which is the value of the corresponding function at 0 and psi 0. And you will have iterated integrals dw, say, j1 s1, s1 dw j2 s2, 0 s, say, k minus 1 dw j k s k, where dw0 is just dt. This is ordinary integral. And j1 jk from 0 to 1 and just dw. So now we can have a way to produce different numerical schemes. So for small t, we want to replace our xi with a truncated sum, a truncated series. So we will take a part of this series and we will try to estimate the remainder. And depending on which level this truncation, at which level we stop our applications of the Ito formula, the order of the scheme is defined. The order of the scheme is defined by the level of truncation. And now for small t, this is obviously going to be like t squared. Now, this is trickier. We know that the mathematical expectation of the square of a stochastic integral is t. So one can expect that this gives 1t and gives like half of a t, which is not entirely true, but it roughly works. Now, this kind of gives 1/2 here, and by half here, this just gives t. So in some sense, one can think that this is of the same level of importance in this part, which is not entirely true in the stochastic setting, but this explains how you calculate the order of the scheme. So if you consider reminders of such term and you want to say that this scheme of some order, all Lebesgue integrals count as 1, all stochastic integrals count as 1/2, and that leads to schemes of 1.5 order, 3.5 order, etc. So compared to the deterministic case, you don't get this 1/2s, and you have first order scheme, second order scheme, etc. But here you have flexibility. You can sometimes decompose such integrals, sometimes you cannot, you can avoid decomposing them, etc. Now, this is slightly a rough explanation how it behaves. We will see that it's not a pathwise behavior. This is L2 behavior, but the pathwise behavior is somewhat trickier. So the characteristic feature of this expansion is that we have iterated integrals of this form, And we have derivatives. So this all introduces higher order derivatives of the original coefficients, which is obviously might be problematic in practice. So in fact, if you look at how people are trying to model specific schemes, they often cannot use higher order schemes because their derivatives are problematic. Sometimes they use so-called implicit schemes. We might have time to speak about them in the end of the course. In the very same way, implicit schemes for ordinary differential equations appear. So if you have stiff, so-called stiff equations, you cannot use explicit schemes. You can use just Euler method. You need to go for the implicit Euler method, etc., etc. Also, the level, the order of the scheme you want to obtain heavily depends on what you want to achieve. In general, the consensus is that it's not really worth going, it's rarely worth going upper than the first scheme, the first order. However, because we have this part, you can try doing the scheme, taking this into the remainder. So this is the remainder in the first method, or you can use try to use this integral to define a scheme still, because this is smaller, this is smaller, this is definitely smaller. So this may be important for getting better approximations compared to the case when you just forget about everything except for this part. And this actually leads to two effectively main schemes. So the first one is the Euler Maruyama Maruyama scheme. And this is exactly what happens when you forget about everything here. You just take the linear part. So to formulate it, let us introduce everything happens on this interval. And we will introduce uniform partitions of the 0t. So 0 is going to be t and 0 less than t and n equal t. T and k is just k divided of t capital for all n. And we define the Euler-Maruyama scheme as follows. So let's introduce delta n. This is the size of the partition at step n. Delta w and k is the difference of the values now. In practice, obviously, we are not having a Brownian motion. These are just Gaussian independent variables. So again, if you look at this, that means that the value of our scheme on the next step should be the value of our scheme on the previous step, plus the value, the time step, and the stochastic step. So eta n k plus 1 equals eta n k. This is like psi 0 plus a t n k eta n k. This is exactly a 0 psi of 0 time step plus sigma t and k eta and k delta w and k, where k ranges from 0 to n minus 1, and eta n0 is just where we start. So this is our scheme, and this is effectively independent n0 delta n random variables. So this is the first scheme. Now let's formulate a scheme that neglects this part, neglects this part, but tries to do one more decomposition of this. So we will use the Ito formula to this part. We just give the constant equal at the value of this operator at the point 0, psi of 0, and we'll get iterative stochastic integral. This leads to another scheme, which is the Milstein scheme. And note that L1 sigma r psi of r, it's now sigma with respect to second second variable, because L1 was defined as this sigma delta x. So now, using the same notation as the previous example, we get the same linear part at nk delta n plus sigma t nk at nk delta w nk plus sigma squared at tnk at nk, not squared, but the derivative with respect to second argument. And here we have integral from tnk plus 1 dws, formally integral from t and k to s dwr. Let's have a look at this expression, because we actually know how to calculate it. dws, actually ws minus w t and k. But this, we already know that integral from 0 to t wr dwr is just wt squared minus t divided over 2. We calculated that a number of times, especially when we are proving some properties of quadratic variation of a linear trajectory. So now we start instead of 0 from this point, but here we exactly have a linear process that starts from this at this new time. So this is effectively 1/2 delta w nk squared minus delta. So now we can rewrite the scheme. A delta n plus sigma delta w nk plus 1/2 sigma prime with respect to second argument delta w squared n k minus delta. You can go in one-dimensional case further, because actually you can calculate all iterated derivatives, iterated integrals with respect to one Brownian mesh in terms, for instance, Hermite polynomials. They are like literally known, and there is a recursive formula for them. However, what is the problem when we consider multidimensional case? Multi-dimensional case. You will need to define new L0, which is going to be dt plus a times nabla plus 1/2 ag sigma g. Here we have square, so now we will have like do not want even to write it down, to be honest. It's a bit pretty. So in multi-dimensional case, just let's do it simpler. You will still have the Ito-Taylor formula. It's going to be messier with a lot of deltas, with a lot of sigmas. Sigma is going to be a matrix. You will getting components of those matrices multiplied, etc., etc. But what is important, if you're going to do this decomposition, instead of integrals of this form, you will actually get integrals of slightly different form, in the sense that you will still get dwj1 s1 integral from 0 to s1, dwj2 s2 integral from 0 to s k minus 1 dwjk sk, and again, if we have 0 is just dt, but dwj is going to be a proper stochastic integrals, and we are going to have independent, in multidimensional case, independent Brownian motions. So you will have iterated integrals, but with respect to different Brownian motions, and no analytical expressions are known in general. And that's actually a big problem. In one-dimensional case, you can try to calculate them. But in multi-dimensional case, you do not know what these integrals are. And if you want higher order schemes, you must include such things into your scheme. But it's not clear how to calculate them. And recall that it's already a scheme. You are already living on a small time scale. You are already living from tnk to tnk plus 1. So doing another discretization to calculate such integrals is also not very easy, but it's how it's done often. You will introduce another sub algorithm that is invoked on the whole step of your original scheme to calculate such integrals. Obviously, it's going to increase the complexity of your system. Now, I will write down the Milstein multidimensional scheme, to show how it looks at least. And also because I have it written down in my notes. So since sorry, just sigma, xi, dwt, where xi, ak, like the sum from j to 1 to m, sigma jk, dwk. K, J, G. Now Xi lives in Rd. A is a function R plus time Rd to Rd. It acts on this pair and gives us a value in this space. Sigma is function again exactly of this form. But it also must now act Rm, where W1, Wm are independent Brownian motions. And now, if I am not wrong, let's set sigma k, sigma j k, j from 1 to d. It's a vector in R. JDs are M, and sigma prime k is typical notation, is the zero for the Jacobian of this expression. J sigma k. Now E should be the first. Okay. And the Milstein scheme then can be written down as, okay, this is R-dimensional, D-dimensional scheme plus A T-N-K eta N-K delta N plus, and here we will have a sum over L J from 1 to F sigma L sigma G, product of two matrices, calculated T-N-K eta N-K. And here we'll have integrals I was talking about. T plus 1 WLS minus WL TNK, TNL, TNK, sorry. DWG of S. So where L and G are different, you can actually see that it's not clear how to calculate. And this is a problem of all high order scheme. Sometimes actually, if this matrix satisfies some commutativity assumptions, everything is much easier to do. Now, before now establishing some rigorous results about the convergence of this scheme, let's do a divergence and speak about, recall what is happening in deterministic case. So the standard approach to numerical schemes in deterministic settings is the following principle: consistency plus stability imply convergence. This means that our approximation at small time is good. So we take, for instance, a linearized version of our original differential equations, everything good. Stability controls how local errors are propagated. Now, this scheme is actually still works for SDEs. And there is the whole, but now it will involve second moments. And if we return to the Ito-Taylor expansion, you will see that if you go for higher order schemes, you will get more and more such integrals. There is actually a neat way to write them down in a unified manner, and that is why it's called Wagner-Platen expansion, because these are the guys, at least I think so, who did this and introduced some formalism for working with such integrals, and you can estimate them in a unified manner, and you can get some nice estimates for reminders, etc., etc. Now, returning to this, so what does this mean? So assume that we have such X is an original process we want to simulate. Original process. And we have some numerical scheme that is supposed to produce an approximation. It's roughly speaking the value of our original process. And then formally, there is the following decomposition. So J from K plus 1 to N minus 1 RNG. This is our approximation scheme. E N K P0 T and K of X0, where P0 T and K acting on X0 is just the value of our process T and K. This is the operator that solves the original problem, that produces the value of x. So you can just write here t and k. And e and k is actually a local error. This is the value, what happens if we do our linearization. Let's think about such version at the case step. So you need the original problem to be more or less stable, so this is controllable. You have consistency, so the local error, which is exactly in our case, all these four integrals, this is the local error, because we replace this with this part, linear version. This should be small, this is called consistency. And now this should be controllable. So the local error gets propagated in a controllable manner. So this is called numerical stability, because sometimes stability also means the behavior of the numerical scheme when t goes to infinity, etc., etc. Now, this is a deterministic scheme. While it can be used in the stochastic setting, it's not, in some sense, the best way to do it. It's questionable in the sense that you can still work with such things, but there are more native to probability waves. However, when we are going to speak about weak schemes and approximation of functionals of solution to stochastic differential equation, this is something we will encounter again. And in the stochastic setting, the proper way to discuss consistency is to include second moments. So I will just formulate the idea what is. So consistency in this analog of deterministic principle is as follows. So given a numerical scheme at nk, we don't care how it really works right now. Stability means that there exists a deterministic function, positive, such that three things happen. Obviously, it converges to zero when delta goes to zero. Secondly, we have control in the square mean at k divided delta n f t and k conditional expectation at. This is a full analog of a deterministic part, but in the deterministic part you don't get this conditional expectation, you don't get any expectations at all. Squared should be less than f of delta, and you need also to control the variance of your scheme in the sense that this minus this minus conditional expectation almost recreates the variance of the original equation at small times. Delta w and k, everything squared, is also less than f of delta. So if this happens, you can go for very similar calculations to prove that your scheme is convergent, and you can obtain the rate of the convergence in terms of this f of delta. So very trivial exercises, the Euler-Maruyama scheme has actually f equal to 0. It doesn't mean that it's exact, because the error of this scheme is not going to be less than 1/2, actually. And we will see the next time that the Euler-Maruyama scheme has the order of convergence of 1/2. The Milstein scheme has the order of convergence 1. And later in the course, we will see that for weak approximations, these schemes are actually equivalent. Both have first order of convergence. And this is an interesting point, that the rate of convergence for weak schemes is, generally speaking, better than the rate of convergence for strong schemes, because you don't need to replicate the behavior of the Brownian motion. And Brownian motion has very irregular trajectories, and you have problems replicating those properties. Now, another interesting observation here, just for general knowledge, that because you have here the sum, generally speaking, if you have local constituents of order n alpha, the whole scheme is going to be convergent with order alpha minus 1. So it's not immediately clear why we get, for instance, for the Euler-Maruyama scheme, something good, because it seems that it's of first order only locally. It still is going to converge it, and we are going to establish good rate of convergence in L2 sense and also pathwise. This is the time to stop. And does anyone have questions? Okay, so no questions.